In the last video, I talked about using the regression standard error S to evaluate the fit of a multiple linear regression model. In this video, I'll talk about using the coefficient of determination, also known as R-squared, for evaluating the fit of a model. So the idea is the same as it was in simple linear regression. We could imagine that without the model, if we wanted to estimate the response variable y, we would simply use the sample mean m sub y. But because we have a multiple linear regression model, we can hopefully obtain more accurate predictions or estimates of y using fitted y hat values from the estimated regression equation. And so what R-squared is designed to do is designed to measure how much we reduce our error when we do this, when we use the model rather than simply estimating y with the sample mean. So we defined these quantities in simple linear regression, and the definitions are exactly the same. We can calculate the total sum of squares, which is the total error without the model, and that's the difference between y and the sample mean squared and added over the sample. So that measures the variation in y about its mean. And then the residual sum of squares, we already defined this when we talked about estimating the least squares equation. The residual sum of squares is the sum over the sample of the squares of the residuals, so the difference between y and y hat. So this represents variation that's unexplained by the model, the variation that's left over. And then R-squared measures the proportional reduction in error by taking the difference between total sum of squares and residual sum of squares and dividing by the total sum of squares. So let's look at an example. So we've got our home price data set with two predictors, floor size and lot size, and this was the model that we fit with floor size and lot size, and then we summarized it, and then we got this output, and right here it tells us the value of R-squared, 0.9717, or to 3 decimal places 0.972. And to interpret that number, we turn it into a percentage, so 97.2% of the variation in y, the sale price about its mean, can be explained by a multiple linear regression relationship between sale price and the two predictors, floor size and lot size. And again, explained is in quotes here because we're not implying any causality here, and so sometimes people will say accounted for instead of explained here, just to emphasize that point. So in general, R-squared measures the proportion of variation in y about its mean that can be explained or accounted for by a multiple linear regression relationship between y and the predictors. And if we think about a couple of extremes, if the total sum of squares was the same as the residual sum of squares, then R-squared would be 0. We can see this just by looking at the formula. This part would be 0. And so that means that using the predictors to try and help me understand the variation in y hasn't helped at all. And we might as well just use the sample mean if we want to predict or estimate y, regardless of the predictor values. So that's one extreme. The other extreme is if our model is perfect and there's no error. The residual sum of squares is 0 and R-squared is 1. And again, you can see that in the formula. If this was 0, then R-squared would be 1. So those are the two extremes, but in practice, of course, we usually get something in between. And in general, a higher value of R-squared corresponds to a better fitting model. So far, this is exactly the same as it was in simple linear regression. But when we move to multiple linear regression, we have multiple predictors, and a little bit later on in the book, we're going to talk about model building, And that's the idea of what is the best combination of predictors to use in a model to help me understand variation in y, to help me predict y, to help me model that relationship. And in particular, should we use all k predictors? Or is a subset of the predictors actually more effective than using all of them? So you might think, well, just use them all, what's the harm? But it turns out that using too many predictors when a smaller subset is sufficient, using all of the predictors is actually problematic because it can lead to overfitting, and we end up actually not being able to predict as well as we can with a smaller set of predictors. So to think about this idea, we're going to consider a sequence of nested models, and each model in the sequence just adds predictors to the previous model. If we wanted to use R-squared to tell us which of that sequence of models is the best, then it turns out that R-squared will simply say, well, use all k predictors. And why does it do that? Well, the intuition behind that is, imagine that we start off with a simple linear regression model. So we've just got a two-dimensional scatter plot. The predictor is on the horizontal axis, the response is on the vertical axis, and we fit a least squares line to the data, and that leads to a particular value of R-squared. Now suppose we add a second predictor. So now we can imagine moving to a three-dimensional scatter plot where that second predictor is one of the two predictors and the original predictor is the other predictor. And now, instead of a regression line, we have a regression plane. And that regression plane is designed to minimize the residual sum of squares. And so you could imagine that because we now have a second predictor, we can move that plane, and we've got a little bit more flexibility how we move it. We can actually get a little bit closer to the points than we could when we didn't have that second predictor, and we just were able to move the line. Having a plane now gives us a little bit more freedom to minimize the residual sum of squares, and so we can, at worst, do just as well as we did before, but generally we do better than we did before. And so the residual sum of squares for the model with two predictors is less than or equal to the residual sum of squares for the model with one predictor. And because the residual sum of squares is less than or equal to what it was before, the value of R-squared is greater than or equal to what it was before. And so what this means is that every time you add a predictor to a model, R-squared goes up, or at worst stays the same, but generally goes up. And so this means that R-squared is not a useful criteria for deciding which is the optimal subset of predictors to use, because it will always say just use all of them. And we know that that's not generally the best solution. Usually a subset of predictors will be optimal. So to get around this problem, we need to penalize models that have too many extraneous predictors in them. Predictors that aren't adding useful information, they're actually just adding noise. So one measurement that does that is something called adjusted R-squared. So it's a way of adjusting the value of R-squared to penalize for models that contain too many unimportant predictor variables. And it's given by this rather ugly looking formula down here. And what this does is it provides a measure that can be used for model building purposes. It's one way that we'll actually talk about many different ways of doing model building, but this is one way of model building, is look through the models and find the one with the highest value of adjusted R-squared, and based on that criteria, that will be the best for modeling the relationship in the data. So there's two different versions of R-squared that are relevant in multiple linear regression. There's regular old R-squared, and that's got a nice clear interpretation. Simply represents the proportion of variation in y about its mean explained by the multiple linear regression model, or accounted for by the multiple linear regression model. So it's useful from that perspective, but it's not appropriate for model building. So the other measurement that is appropriate for model building is adjusted R-squared. So both of these values have value in a multiple linear regression analysis, regular R-squared and adjusted R-squared. So we can see the value of adjusted R-squared in the output for our home prices example, so 0.9528. There's no useful interpretation of this number as there is for this number, for R-squared, but it would be useful if we were model building. So to illustrate, let's fit a second model just with floor size and summarize that. So we can see that this model has an adjusted R-squared of 0.6029. The model with two predictors, floor size and lot size, had an adjusted R-squared of 0.9528. So based on that criteria, this model with two predictors is better than the model with one predictor. And so what this tells us is that adding lot size to a model with floor size doesn't lead to overfitting and results in a worthwhile addition to the model, having that extra predictor in there. You can also see, I've got the results summarized up here. The model 1 is the model with just floor size. Model 2 has floor size and lot size. And we can see the values of adjusted R-squared increasing from 0.603 to 0.953. We can also see R-squared increasing from 0.682 to 0.972, but that in and of itself is not interesting because, as we argued a little bit earlier, that always happens, or at worst it stays the same. But we can also look at the values of S. So the regression standard error has decreased from 7.178 to 2.475. So we're going to get much more accurate predictions with the second model than the first. Let's look at another example with a few more predictors just to see how useful adjusted R-squared is. So this data is from the shipping department of a company, and there's 4 predictors in this one. There's, well, labor hours is the response variable, and then TWS is the total weight shipped in thousands of pounds, that's X1. PST is the proportion shipped by truck, that's X2. ASW is the average shipment weight in pounds, that's X3. And week just keeps track of the week, and that's X4. And we're going to compare two models. One model has X1 and X3 in it, and the other model has all 4 predictors in it. So here's model 1, and we'll summarize it, and we'll note that the value of adjusted R-squared is 0.7715. And here's model 2, which has just X1 and X3, or TWS and ASW in it. And that has an adjusted R-squared of 0.7857. So that value of adjusted R-squared is actually larger for the model with just 2 predictors. The model with all 4 predictors was 0.7715, and model with 2 predictors is 0.7857. So what this tells us is, so I've got this summarized here. Here's the 0.786 for the 2 predictor model. Here's 0.771 for the 4 predictor model. That tells us that the 2 predictor model is better than the 4 predictor model, at least according to this adjusted R-squared criterion. So in this case, that does suggest that the other 2 predictors, x2 and x4, that aren't in the smaller model, if we were to add those, that would cause overfitting, which is not a good thing. What about R squared and S? Well, if we look at R squared, of course, it's larger for the bigger model, the model with 4 predictors. But again, that's not interesting because that always happens, or at least it would be the same. At worst, it would be the same. The regression standard error, that's kind of interesting in this example. With 2 predictors, 8.815. With 4 predictors, 9.103. So the smaller model is getting more accurate predictions. So that lines up with our finding that adjusted R squared is telling us that the 2 predictor model is favored as well. Okay, I'm going to end up this video with a brief discussion of correlation, because when we talked about R squared in simple linear regression, we noted that if we square the correlation between y and x, that's the same value as the coefficient of determination R squared for the simple linear regression of y on x. So that doesn't quite carry over for multiple linear regression because now we have multiple x's. But there is a correlation that has this relationship that when we square it, we get the value of R squared, and that's called the multiple correlation coefficient, or multiple R. And that measures the correlation between the observed y values and the fitted y hat values from the model. And sometimes this is given in statistical software output. If we look at R, it's actually not given, but there is software that does provide it, and I've provided it here in this summary table. And if I square that number, I would get the value 0.972 R squared. So that's a concept that we talked about in simple linear regression, and it was quite a useful idea. But it turns out that if we get too caught up with correlation in multiple linear regression, it can actually lead us astray. And I'm going to give a couple of examples of that we'll return to in a later video. So if you were to look at this graph, so this measures sales and advertising. One summary of this graph would be, well, there's very little going on there. There's not a lot of correlation between these 2 variables. So you might think, well, advertising isn't going to help me predict sales. It's not going to be a useful predictor of sales in a multiple linear regression model. Turns out that that is false. Turns out that this data set from which this graph was derived, turns out that advertising is a useful predictor of y in a multiple linear regression model. So just because we've got low correlation between y and a potential predictor does not necessarily mean that that predictor will not be useful in a multiple linear regression model. Turns out that this can go the other way as well. So if you were to look at this graph, so this one is sales and advertising in traditional marketing arenas, so newspaper, television, that kind of thing. Very strong correlation between the 2 variables. And so you might think, well, if I was to use traditional advertising as a predictor in a multiple linear regression model, it's going to be awesome, because look at that correlation. Turns out, though, that when we look at the data from which this graph is derived and have a multiple linear regression model with this as one of the predictors, it's actually not a good predictor. So just because we have high correlation between the response variable and a potential predictor does not necessarily mean that that predictor will be a useful one to include in a multiple linear regression model. So I just wanted to end up the discussion of R-squared with that brief discussion of correlation, because it's a concept that can lead you into trouble in multiple linear regression, because there's a lot of things going on. So we've talked about two ways of evaluating the fit of a multiple linear regression model now: the regression standard error S and the coefficient of determination R-squared. In the next 3 videos, we're going to focus on thinking about the regression parameters in the model, so B1 and B2 and so on.